Hello, my name is Davy van Wingerden, and I will be presenting my project on the potential of aerogels for orbital debris remediation. So just to start off, orbital debris remediation is just the removal of space junk in Earth orbit. The problem, despite the increasing risk orbital debris has posed to future spaceflight, Earth's orbit is continuing to become more congested with satellites. Elon Musk's Starlink mega constellation plans to deploy nearly 42,000 satellites into low Earth orbit, and this is a dramatic increase from the approximately 10,000 satellites currently in low Earth orbit, 4 times the number. And the growing presence of Starlink satellites has already increased the frequency of collision avoidance maneuvers, highlighting the need for intervention. And this rapid growth in orbital debris is partly attributed to the increasing frequency of space launches that rely on non-reusable rocket boosters. Additionally, collisions between satellites further highlight this problem, and they can potentially trigger the Kessler syndrome, which is a self-perpetuating loop of continued orbital debris collisions that will pretty much create a wall of debris around Earth orbit, making it impossible to pass through. And while reusable rocket boosters can mitigate the debris to some extent, like with SpaceX's Falcon 9, even small fragments like flecks of paint can endanger spacecraft and satellites. And if this issue is left unresolved, the growing orbital debris population can jeopardize not only the future human space exploration, but also the continued operation of satellites that are crucial to communication, navigation, and Earth observation. Now, while collisions between satellites are uncommon, the probability of one occurring is increasing. In February 2009, the Russian satellite Cosmos 2251 collided with Iridium 33, and this generated hundreds of thousands of pieces of debris. Additionally, anti-satellite tests, or ASATs, are becoming more common, and several of these tests have been conducted by Russia, India, and China. And these are essentially controlled collisions between two orbital objects, and this continues to add ever more debris. Now, numerous solutions have been proposed to address this challenge. Such solutions include magnetic manipulation of space junk, the use of harpoons to spear debris, and other drag augmentation systems. I wanted to take a more chemical perspective of this problem, and I wanted to look at this through the use of materials, and so I began examining the potential of aerogels to clean up space junk. Now, what are aerogels? Well, they are the lightest material ever synthesized by humans. The densities range from several millions to around half a gram per centimeter cubed. And they are microporous solids that are created by removing the liquid from a gel structure. So imagine this like a jello, but without any liquid in it. And that's sort of the image that you see on the bottom right. And the most common aerogels are silica, but you can also get alumina and titanium. Aerogels have gained prominence in the aerospace industry, particularly for thermal insulation on spacecraft. Notably, they were used for the Space Shuttle installation tiles due to their extremely low thermal conductivity. Their unique microporous structure not only makes them efficient for the insulators, but also presents an innovative solution for orbital debris. And this unique microporous structure comes from the manufacturing process. So in essence, you're combining a silicon alkoxide with water and then usually an alcoholic solvent. And you're creating an aggregate of silicon nanoparticles to create a gel. Hence the name aerogel. But then to eliminate impurities, you will basically use pure alcohol to purify the um, gel, and then you will obtain the final product by using supercritical solvent drying. And this essentially will evaporate all the liquid inside, but keeps the solid shell. Now, what's left is a intricate network of interconnected nanostructures. And when this interacts with a particle traveling at 17,500 meters per second, there's going to be thousands of microscopic breakages within the aerogel structure, and this kind of goes progressive energy dissipation through the loss of kinetic energy and then also transferring of mechanical energy to the aerogel. Now, this is not a completely novel solution. Aerogels have been used to capture deep space comet dust. And the Stardust mission, which was launched in 1999, was the first mission to safely return the cometary samples. And there was an arm that would extend behind the spacecraft, and that would essentially capture the comet particles. And the tracks can be seen on the right. Now, for this proposed mission, this would be used in an emergency situation when there's a significant volume of orbital debris, such as during a satellite collision or an anti-satellite test. And we'll have 10 of these spacecraft deployed to essentially traverse the resulting debris cloud. And there will be aerogel bricks that are positioned on the fore section of each spacecraft, and these will sort of act as a shield, capturing as much debris as possible. The mission will then last for around a year, and then the spacecraft will deorbit and re-enter Earth's atmosphere, and this ensures that the collected debris is safely removed. The spacecraft design is heavily modeled on the Stardust spacecraft. It's going to be around a bus or a refrigerator size spacecraft. There will also be the aerogel collector, which in the image is that very large blue circle, and on this is lined with bricks. And we found that while the radius of the unfolded collector is far too large for it to fit onto the spacecraft, through the use of innovative origami that's being studied by Jet Propulsion Laboratory, we can actually collapse the collector into a smaller circle of around 1/9 of the radius, so around 0.6 meters. And this will allow for much more efficient storage. For maneuvering, the spacecraft will have cold gas thrusters as well as attitude orbit control systems to essentially manage the orientation of the spacecraft. And to protect the collector during launch, there'll be a small circular door that's placed over the collector, and that will be removed after launch. Now for mission operations. For this specific project, or for this specific mission, we'll look at Mission Shakti, which was the Indian ASAT test in 2019. But the placement of the satellites for any given instant is dependent on many other variables, and therefore this is not a sandstone. On the left, there's the image that models the trajectories of the orbital debris after the mission Shakti. And this debris exhibits sort of a banana-shaped distribution around Earth orbit, with the highest concentration in apogees of around 750 kilometers and perigees ranging from 200 to 500. So in other words, the spacecraft orbit would range from 750 at its furthest point from Earth and 200 to 500 at its closest orbit. We'll be placing our spacecraft into the same orbit as the debris that will ensure that we can intersect the debris path, and we will also ensure that our spacecraft will have a larger orbit than the debris. By ensuring that we have a larger orbit, it means that our debris will travel. It means that our spacecraft will be traveling faster than the debris at a closer approach. We settled on the number 10 because if we only sent up one spacecraft, it would take approximately 10 years and around 60,000 orbits to complete, to cover a 300-kilometer stretch. By using 10 individual spacecraft that is systematically sweeping these high-density zones, we can essentially cover a much larger area. And after each orbit, the thrusters will essentially cause the thrusters will fire and it will decrease the orbit radius of the spacecraft by 5.4 meters, which is the size of the collector. This creates like an overlapping sweep, which is going to be much more effective. And for launch, we will use Rocket Lab's Electron launch system, as this offers the necessary capabilities for launching a microsat to LEO. Now, the cost to produce approximately a cubic centimeter of aerogel is around $1. Now, for the calculated total cost of the aerogel collectors for this experiment or for this mission, this would be around $500,000. Now, future cost reductions is anticipated to go down to around $7.2 per cubic meter, which means that the cost of the aerogel collector can be lowered from $500,000 to only $114,000. And while this does seem like a fairly high cost, it is nothing compared to the damage that can be caused to a geostationary satellite or a weather satellite. So in conclusion, aerogels present a very promising solution to the growing issue of orbital debris. Their unique micropore structure, coupled with their successful application in the Stardust mission, makes them an ideal material for capturing of the target-sized debris. Designed to be compact and lightweight, we have reduced the need for extensive transport systems and lowering launch costs. The staggered orbit configuration enhances the efficiency of the debris collections, as well as minimizing the time the satellites spend in orbit. And as the cost of aerogels continues to decrease, and as the threat of satellite collisions increases, these satellites can play a crucial role in safeguarding the future of space exploration. Thank you for listening.
Davy, thank you for that very informative presentation. Now we'll take questions from the audience. If anyone has any questions, please type it in. And while we wait for that, I have a question myself. So Davy, you mentioned that there is an increasing problem with more and more satellites in orbit. Do you know to what degree satellites are expected to increase over the coming years? Are we mostly stable? We sent up 50,000 satellites, and are we good, or will this double, triple over the coming years?
So it's actually projected to increase, mainly due to the kind of increasing desire for satellite constellations, where you're basically having a very large network of microsatellites that are interconnected through waves, as Macarena had just talked about, and those will be used for communications or navigation. But the number is projected to increase. I'm not sure if it's a linear or exponential, but you have SpaceX's Starlink, which you may have seen, like the long line of lights. You've also got Amazon's Project Kuiper, and there's several other smaller rocket private companies that are hoping to perform their own missions.
I see. And I have one more question, which is, you mentioned how we have these collector aircraft that are covering a large area. Do you know if people are putting these aerogels on the satellite that needs to be protected itself?
So currently a lot of satellites do not have very effective ballistic shielding, primarily because of the extra mass that would add on, and that would increase the mass of the actual satellite, which would increase the cost of launch. And it's also extra development time that these private companies probably do not want. I think in the future, um, if this issue were to be more seriously addressed by NASA, SpaceX, Blue Origins, and the other larger companies, it will encourage other companies as well as their own to start incorporating some aspect of shielding, such as maybe whipple shielding, which will not necessarily completely eliminate the effect of an impact if it should so happen, but rather it will very much minimize the damage done. Um, so I think it's not so much about damage. It's not so much of a question of prevention at this point, but rather mitigating the extent of damage and um, solving solutions to reduce the things in Earth orbit and create uh, stop putting in more than we can take out.
Got it. Well, Davey, I have so many more questions, but we are at time. Thank you so much for that illuminating and insightful presentation. I learned a lot, things I didn't know. And for anyone else, if you have further questions, feel free to ask Davey in the chat. So with that, I wanted to thank you again.
Thank you.